this webinar started here. Depending on where you're calling in from, good morning, good afternoon, and good evening. Today, our topic that we're going to be speaking about is, are your proof tests effective? Now, before we get into it, I'd like to explain a little bit about myself, give a little company background, and then we'll get right into the main topic. Like I said, hello, my name is Ted Stewart. I began my professional career with Lockheed Martin, and while I was actually in college, I was working as a test engineer. When I was at Lockheed Martin, I analyzed and I enhanced their earned value tracking PM tools, and I even streamlined a few processes, and this is what actually helped me earn my green belt. I then began working for Harris Corporation, where I started off as a lead manufacturing engineer, and then into the program management role, where I dealt with 20-plus classified products, taking all these products from the development phase into the production phase. I have now worked for Exida for about a year and a half. I'm a safety engineer and also a project manager, and really I focus most of my efforts with the end user in mind and helping our direct customers increase their sales and revenue. As you see here, Exida is a global safety knowledge company, and we're actually a certification body that has a vast network of excellence in dependable automation. We're composed of different people from very different organizations. As you can see here, we have formal development managers, instrument engineers, and even PLC product managers. We're very familiar with the new product development, safety certification, and also system-level design. Now, before I go any further, I'd like to make a comment. We had a morning session earlier, and we got a plethora of questions, really great questions. So what we've decided to do is, please, there's a Q&A at the top of your screen there. Write as many questions as you want, and if you wouldn't mind, we do have the sign-in sheet with everyone's email address. Include your email address at the end. What I'd like to do is I'm going to compile all the questions from this morning and also from the this session here, and I'm going to send everybody an email out with every answer to every question just so that you can have it there with you. I feel that's a better use, and therefore you can always go back to this email that I send after the presentation to use it as a reference point for those questions that were asked. You can have those answers. So please, go in the Q&A, ask as many questions as you want when you feel so. And please note that these questions will be answered after the presentation. Thank you very much. Let's move on. All of our work is very focused on automation equipment, availability, safety, and cybersecurity. Our work is summarized in the following categories that you see in front of you. And we split into 6 simple categories. You have consulting, product certification, training, engineering tools, reference materials, and professional certification. Now, Exida is heavily technically oriented. We do a lot of research on failure rate data and analysis methods, which are used on safety and reliability. We like to think of ourselves as a knowledge company, and we publish most of our research basically online in books. You can find us, as you see there, at exida.com. You can find us at isa.org. You can also find us at amazon.com. So basically, anything that we like to work on, anything that we learn as new knowledge, we will publish it and make it available for everybody to help everybody out. All right, 3 design barriers. Now, there are 3 things that need to be checked when doing a SIL verification. And as you see here, we like to call them the design barriers. The first one is SIL based on systematic capability. The second one, SIL based on PFH. And then the third one is the 1H route for SIL based on architecture constraints. We call it SIL AAC, or you have route 2H. Now, we will be looking at the probability calculation for the PFDavg in a low demand safety application where proof testing can be used. Okay? In calculating the PFDavg, there are 9 key variables to consider. The 9 variables are failure rates of each product, including the failure modes, and any diagnostics coverage from automatic diagnostics. And we're actually going to be touching a little bit about that. redundancy of devices, including common cause failures. There's also the proof test intervals, mean time to restore, proof test effectiveness, mission time, proof testing with process online or shutdown, proof test duration, and operational and maintenance capability. Through this presentation, the main one we are going to be speaking about is going to be number 5, but also note here, as you see as it floated up, the key variables needed for PFD calculation. We actually just did a webinar last week, so if you'd like to know in more depth of all 9 variables, please see last week's webinar, and Dr. William Goebel goes through the entire thing and does a fantastic job. But like I said, today we're going to be speaking, or of those 9 variables, we're going to be speaking of the most important, one of the most important ones, which is the proof test effectiveness. In this presentation, we're going to explain basically how it impacts the PFD calculation, and we're going to do some examples showing basically in excellentia, and then we're also going to have another example after the fact to try to sink in why so many people are focused on a proof test and how they feel. This is how you base a product. In reality, I'm going to kind of show you, maybe shed some light on a difference of mindset on how you use a proof test. Now, as you see here, this is a perfect proof test, which is for a perfect world. However, let's imagine for a minute that we have that ideal scenario. Unrealistic, but it's ideal. Here's a chart that shows you what a perfect proof test would look like. So, what's the probability of failure? If we know there is no failure, well, obviously it would be 0. As you see with the line points, it would be 0. The graph, you can see here, it looks like a sawtooth, but this graph is very unlikely, and we'll go into why. When a condition or demand occurs infrequently and is an independent event, you really have no real knowledge of when it's going to occur. The average probability of failure is a valid way to represent failure to respond to a demand. Okay, so if you don't know where it's going to happen, you have to assume all points on the sawtooth graph and find the average, and that's where your PFD average is going to be. Okay? Now, if I run a functional test and I see the system respond, do we know that everything we need to work really does work? Do we even care? If everything seems to work perfectly, is there a problem? I mean, we all say, this test seems perfect to me, and we move on, but really, is everything tested? A proof test is done where, let's just say, a pressure sensor is isolated and pumped up such that the pressure sensor exceeds the trip point. The remote actuated valve is observed to verify that it moves, right? Well, let's ask the question again. Is everything tested? Well, here's just 4 examples that I came up with that a proof test might not cover, that people might not think about. You know, the valve seat, it may not seal properly. If the response time is not measured, component failure may be causing the speed of response to exceed the process safety time. Process connections to the sensor may be failed, or power supply, the droop wire resistance, may be limiting maximum current, disabling diagnostics alarms. And I listed 4 here. There's many more that I could probably list. But, you know, what are some others that you could think of? Are you really testing everything? Is it 100%? Now let's take a look at an equation of a realistic proof test. Now here's a very simplified approximation. Approximation showing that we have had an estimate of proof test effectiveness, the CPT there. Once the time interval and the mission time are determined, you can begin your calculations. The formula for the initial part of the equation, the du, this part simply gets divided into the part that's detected during the proof test, this first term. I'll put a little check mark here. and the part that's not detected in the proof test, which is over here. That's how you calculate the proof test. This approach gives you a good average over a given mission time. And like I said, we'll go into more details in the next coming slides. Now, it can be clearly and definitively be proven by an example that no real proof test is perfect. We have many examples of failures in products that cannot be detected by fundamentally simple functional proof testing. However, you will still find people that say, hey, if it works, it works. It's surprising to see some of the proof tests and how minimal, rough, we can even say crude that they are. Like the example I spoke about 2 slides ago, there was a basic proof test that instructed the user to put a block on a valve and, well, let's check to see if the valve attempts to move. The issue here, and we've talked about this before, you have no idea if that seat actually seals or not. This proof test is far from perfect. And yeah, that's a pretty basic example, but I'm just trying to build a picture here. You know, what happens if you have an imperfect proof test? What's it look like? Instead of taking the probability to 0 during each proof test, we can take it to some finite value above 0. Let's say, you know, right here. As you can see, the probability grows and grows as a function of the number of proof test cycles, and in this case, is totally equivalent to mission time. So you can see here, as it grows. Okay? Now look at the black line, the PFDavg line. I'll put a little check mark there. That is for the number for just one cycle. What we really need is an equation like we saw in the last slide. All right? We need something where we need countless examples show that between the black line and the red line, this little change could actually result by a whole still level. Okay, as an example, let's consider a high-level protection safety function. The proposed design, let's say, has a SIL2 target, and we've chosen a SIL3 capable level transmitter. We've chosen a SIL3 level certified safety logic solver, and a single remote actuated valve consisting of a certified solenoid valve, a certified Scotch yoke actuator, and a certified ball valve. Now, some people say, well, why did you choose all that certified stuff? Well, now we don't really have to worry about the systematic capabilities. For this example, anyways. We're going to use Excellentia, the SIL verification tool, but we're going to enter variables that are very idealistic, okay? Which basically means very unrealistic. But just for this sake, let's just go through the example. We're going to choose a mission time, 5 years. 1 year for the sensor, the logic solver. We'll really have good automatic diagnostics, we'll say. We'll do 100% proof test, which is commonly used, but very unrealistic. And we will assume the proof test is done with the process offline. If it's not online, there can't be a PFD because, well, there can't be a demand. That eliminates the whole worrying about bypassing. So the question now becomes, what do you think the PFD average will be for this example? Is it going to be SIL 1? Do you think it'll meet SIL 2? Or does it meet SIL 3? Let's find out. Here's what we have. In this unrealistic example, we have a PFD average of 6.82 e to the minus 3. This meets SIL 2. It meets it with a risk reduction factor of 147. Okay, now, mind you, if you can read these small numbers, you can see that the architecture constraints meet SIL 2. I'll put a check mark here. You can see that systematic capabilities meet SIL 2. And you can also see here that the PFD average meets SIL 2. And then, obviously, since they all meet SIL 2, the whole system meets SIL 2. Okay? So why did everything meet SIL 2 and not SIL 3? Or why didn't it meet SIL 1? Let's take a look in a little bit of the numbers. Now, for the architecture constraints, the logic solver was still 2. Excuse me, logic solver was still 3. The sensor part, here's a limiting contributor, was still 2, and your final element was still 2. Okay? So what's kind of neat about this Excellencia tool is you can see what areas are holding you up from achieving a different skill level. Okay? Because let's go over to the systematic side, and you'll see here your limiting factor, everything is still 3, your logic solver, your final element. However, your sensor is still 2. So there's your limiting factor. Okay? Another interesting thing that I've noticed while performing this demonstration is look at that blue area on the left-hand side in the pie chart. Almost the entire PFDavg contributor was the final element, okay, which also has a large role in the mean time to fail spuriously, MTTS, which we like to see high numbers. See over here, the MTTS is 133. Now, what does that mean? That means 1 out of 133 years is what you're going to come out to. Now, that's relatively low. It may sound pretty good, but just think about it. What if you had 10 functions? That makes it 1 out of 13 years. Now, let's really start thinking, what if you had 100 functions? This means 1 out of 1.3 years you have a spurious trip. Keep in mind, you need a high number to avoid really costly false trips. Now, let's pick some more realistic variables. Instead of 5 years of mission time, we now have a more conservative mission time. Let's say 25 years, as you see in front of you. We're going to run the equipment without a major overhaul, which doesn't mean we won't overhaul individual pieces of equipment. For example, valves or seals. These can still be replaced, but it's just not a major overhaul or a rebuild for that matter. The proof test interval will remain the same for the sensor. It'll remain the same for the final element, and we will remain the same for the logic solver. Now, the proof test coverage is important. We're going to say 90%, which is pretty good proof test for the sensor. We're going to say 70% for the final element, which can be a little optimistic if we were to say the final element was, for a tight shutoff application. So let's say, for this example, it's not a tight shutoff application. Okay. The proof test duration is now 2 hours. Most likely this should be a little higher with process online, but let's leave it at 2 hours for now. The MTTR, 48 hours, which seems reasonable. We feel within a 2-day span, if there's a holiday, someone can get over there and fix that. I think it'd be kind of unlikely to get anyone out there any sooner than that. And finally, the maintenance capability that we've chosen, we chose medium for the sensor and final element, and we chose good for the logic solver because logic solvers have been very reliable. And so, how do you think we look in a more realistic atmosphere? What's going to happen to the PFDavg? Remember, we had a risk reduction factor of 147 in a perfect world. So let's take a look. Look at those numbers. Wow. The calculated PFDavg for the SIF equals 5.76 e to the minus 2, which barely meets SIL 1 with a risk reduction factor of 17. Kind of interesting when you put realistic numbers in there, huh? Now that we've seen this drastic difference, one can argue that every company that performs their own calculations needs to have a competent engineer who understands the true risks in a real-world situation. And not really one that's biased and thinks the product has 0 flaws and lives in that perfect world. So you can see the importance here. Now that we've learned about how a realistic proof test can affect a product, how can we create an effective and realistic proof test? When creating a proof test, there are a few questions you must ask yourself. First one, how does this component failure impact the product? Is this failure detected by automatic diagnostics? If not, is this failure detected by the manual proof test? Once a proof test is created, now we need to figure out how do we measure the effectiveness of that proof test. Proof test effectiveness is typically expressed as a percentage of DU failures in a product that are directed by a given proof test. Proof tests range from 0 to 100%, many of which are 40 to 90% range. Now, it should be understood that a manual proof test is done to detect failures not detected by automatic diagnostics. Now, tests designed to detect the same failures as the automatic diagnostics, what's that do? That just really consumes time, it increases costs, and accomplishes very little. Here's an important note. And this is, I'm going to start talking about a few things that these past 2 months, many questions have been brought up, and that's actually what geared us towards this webinar, because we're trying to bring an awareness here. As automatic diagnostics get better, okay, manual proof test coverages, they go down. This is good. Let me read that again. As your automatic diagnostics get better, many proof test coverages go down. Okay. This is good. Why? Because the total detected DU failures, those that are detected by the automatic in manual testing, they increase. All right, because they increase meaning they're detected, and the PFDavg drops. Now, you ask me, what is an accurate method of predicting proof test effectiveness? Well, one accurate method of predicting the proof test effectiveness is to review every component, all components in a product by failure mode, and to record or test if a particular manual proof test will detect the particular component failure. Here at Exeter, this is done during our FMEDA process, or failure mode effect and diagnostic analysis. And I do see that we do have a question that came in, and if you don't mind, I'd like to answer this, and I'm going to add it to the stream of other questions that we have. So, and I do appreciate that, Matt. Thank you very much. I will answer that proof test. You'll get an email shortly after this webinar. Thank you. But let's move on to a proof test example to show how having excellent automatic diagnostics plays a big part into a manual proof test coverage. Okay, so here we go. Pretty basic example, but it makes a really big point. Product 1 and Product 2 both have 100/5 of dangerous failures, and both use the exact same proof test. Product 1 has a poor automatic diagnostics with a proof test coverage of, say, 80%. Sounds great, right? 80%, hey, that's not too bad, that's respectable. Product 2 now, it has a good automatic diagnostics with a proof test coverage of 20%. Now, many people, if I say, hey, your proof test coverage is 20%, they get upset, they get mad. This seems really low. But which product is safer? Which is more reliable? Which product would you purchase? Okay? And we have, some of our customers, they're looking for 100% proof test coverage. This is where we need to tell them and show them these examples. Let's look at the left column only. Okay? The proof test covers is a measure of how many undetected dangerous failures are detected by that proof test. Okay, product 1. It has 100/5 of dangerous failures. The automatic diagnostic support, it detects 10/5. You see there, lambda DD equals 10/5, the lambda DU equals 90/5. And for our example, the manual proof test, let's say it can detect 72 of these 90/5. The proof test coverage now, say 72 over 80, or 72 over 90, 80% proof test coverage. Hey, not bad. However, as you can see here, there's still 18/5 that were undetected. What if a product had good automatic diagnostics? It can detect 90 of the 100/5. Well, your DD is 90, your DU is 10/5. Now, the same manual proof test as before, but the automatic diagnostics now finds 70 of the 72. The new proof test now detects, the manual proof test now detects 2 of the 10 that are outstanding, which is a 20% proof test coverage. You see here, the one that sounded great with the 80% proof test coverage, you still have 18 fits that were undetected, whereas the 20% proof test, you only have 8 fits unprotected. You know, you never want to use a proof test coverage as a measure of quality for a product. So when someone asks, hey, I want this product, but I want a 95% proof test coverage, do they really know what they're asking for? Do they look into what that product has for automatic diagnostics? You know, and when we normally see the different proof test coverage, we can actually sometimes find that the opposite is true, that the lower proof test coverage actually is the better product. But let's say, not in all situations, but we just at least want to make sure that people can see how this can be. Okay? And here's a little summary, right? So, a realistic PFDavg calculation. It depends on several variables, as you saw, including the proof test coverage. Which is actually, last week, we actually spoke about this at last week's webinar. And Dr. Goebel went into great depth with the different variables. The second thing is the proof test coverage can impact PFDavg by an entire cell level. So keep that in mind, depending on how you enter your information. Be careful. Proof test coverage also can be measured by a detailed examination of the product. Now, many people say, well, what was it? People basically ask, well, how do I come up with my proof test coverage? Well, how do I know what my percentages? And really all starts from performing an FMEDA. Okay, and using, here's another thing, the commercial SIF verification tools. Now these have databases of proof test coverage already built in. There's also generic books that are published that can give you a starting point or where a proof test, what a proof test coverage would give you depending on your certain situation. Now here at the end, now that I went through this presentation, I didn't want to make it real long because I know everyone's very busy, but I wanted to get my point across. I would love for you to now take the time to think about this presentation and to write down as many questions as you can in that Q&A at the top. What I'm going to do after this is I'm going to summarize the email. I have everyone's email from the list. If you did not include your email when you signed up, please do so in your question, and I will send out every question with every answer. Therefore, everyone can take this with them and hold on to it for a reference for down the road or whenever you want. Instead of just speaking to everybody here online, I'd like to do that offline. So if you would, take a few minutes now. I do appreciate everyone's time. I will run through just in case it wasn't a webinar-specific question. And as I see here, Matt and Javid, thank you for those questions. I will get those answered most likely today, if not early tomorrow. It's 4:30 p.m. where I am. So yeah, please have the questions come on in. We had about 10 questions last webinar, so I'd like to add and get some more questions here, and we'll go from there. Thanks everyone. I really appreciate it. Go ahead. There's my email address too here if you have any direct questions that you think of after the fact. tstewart@exit.com. Thanks again for all of your time. I really appreciate it. Take care.